Hello everyone, this is Siddiqur Rahman and welcome to the continuation of the fifth lecture of the second week. So let's begin. By the end of this lecture, you guys will be able to convert binary number into the equivalent octal number. So let's move into the next slide. This slide represents the overall scenario of this lecture. You may learn many things from this lecture, such as how to convert binary to octal, example of indirect method, example of direct method, and so on. So let's move into the next slide. First, we need to know how to convert, or what is the overview of the conversion about binary to octal. So let's start. Octal number system provides convenient way of converting large binary numbers into more compact and smaller groups. There are various ways to convert a binary number into octal number. You can convert using direct methods, or you can convert indirect methods. First, you need to convert a binary into other base system, such as decimal or hexadecimal. Then you need to convert it octal number. So let's move into the next slide. And here is an example of indirect method of the conversion. So let's start with the question: what is 10010110 binary number in the equivalent octal number? So this example splits two parts. First part, we need to convert the provided binary number into a equivalent decimal number. After that, the found equivalent decimal number is converted into a octal or into equivalent octal number. So let's begin with the first part. First part and first step: convert the provided binary number into the equivalent decimal number. We can write 10010110, and from the rightmost is the representation of LSB, and the leftmost is represented at the MSB. So start with the right one, 2 to the power 0, which is represent the notational, I again repeat, 2 to the power 0 is the representation of positional notation. We already known these terms from the previous lectures. So 2 to the power 0 into 0 plus 2 to the power 1 into 1 plus 2 to the power 2 into 1 plus 2 to the power 3 into 0 plus 2 to the power 4 into 1 plus 2 to the power 5 into 0 plus 2 to the power 6 into 0 plus 2 to the power 7 into 1. So what do we get after the multiplication? 128 plus 0 plus 0 plus 16 plus 0 plus 4 plus 2 plus 0, which gives us a single decimal number, and which is 150, and this is the equivalent decimal number of the given binary number. So let's move into the next part, which is second part and second step: convert the found decimal number into the equivalent octal number. So let's start. As we know, the found decimal number is 150, and we need to convert the found decimal number into the equivalent octal number. So we can write, and we can write 150 is equals to 2 into 8 to the power 2 plus 2 into 8 to the power 1 and 6 into 8 to the power 0. 8 to the power 0, 8 to the power 1 and 8 to the power 2 is the positional notation. Sorry, I again repeat, 8 to the power 0, 8 to the power 1 and 8 to the power 2 is the positional notation representation. Since this is the octal number, that's why we use the base is 8 for the octal number. And 6, 2 and 2 is two arbitrary number. To get the decimal number is 150, and we write only the left number of each parenthesis, like 2 into 8 to the power 2. In here we can choose, or we can choose just 2, not 8 to the power 2. That's why the second step we get only 2. Second, from the second parenthesis we also get 2, and third parenthesis we also get 6, which is equivalent to 2 to 6, and which is equivalent the desired octal number and of the given binary number. So that's all for this example, and let's move into the next slide. And this slide represents a conversion table in between binary equivalent to the octal digit value, which is, if we say the octal number is 4, then the equivalent binary number of 4 is 100, and so on. So let's move into the next slide. From this slide we may learn another example of the conversion, and this time we get the direct method. Let's start with the question: what is 1010111100 binary number in the equivalent octal number? And direct method means if we look at the solution section, then we can understand here is a figure, or you can say the representation of visualization, and we get the given number is 1010111100, and if you see the rightmost 0 is the 0th position, and which is in the LSB, and the leftmost number is 1, which is in the 9th position, and which is MSB. And the second row of this table, you can see that there is additional 2 zeros. This is because to complete the group of 3, we already know from the previous slides a conversion table of octal digit value to binary equivalent. We have seen that there are 3 bits for octal numbers. That's why we add 2 zeros in beside the 9th position of MSB. So we get 001, 010, 111, 100, which is given as 001 is equivalent to binary, 001 is equivalent to octal 1, 010 is equivalent to octal 2, 111 is equivalent to octal 7, and 100 is equivalent to octal 4. You can have a look, or you can match the table whether it is right or wrong. Then we can write 1274, and which is the equivalent octal number of the given number. I hope you will understand the direct method, how to solve or how to convert the given binary number into the octal number. So let's move into the next slide. And this slide represents some of the examples for your homework. You can do by your own at home. So let's move into the next slide. In the next lecture you will know about the conversion of octal to binary. Next. And that's all for this lecture, and thank you so much for your attention, and see you guys in the next lecture. Thank you.